So, as I mentioned before, we're not really going to talk about galaxy birth and death, because those ideas are not really, birth is not really known very well, and death really doesn't happen. On the other hand, we talk a lot about what galaxies do, and what they do is they interact with their neighbors. So studying galaxies, a big part of it is looking at interactions. And the ultimate goal, generally, for looking at these things is being able to work out what initial condition created the shape that you see and predict what will happen in the future. That's the ultimate goal. There's been a lot of work done on this and some really impressive stuff done. But when we see interactions, there's a few features that really stand out that are very common when we see interactions. There's the Antennae Galaxy down here. So the Antennae Galaxy, we believe it's two disk galaxies that are merging together. That's the center of one, that's the center of the other one here. And these tails form, and that's very common to see in interactions, these tails form. I'll explain how that forms in a moment. The top here is a ring structure in this galaxy. This galaxy looks like a disk, but there's a ring that exists in the outer edge of it. Okay, a similar picture is this thing here. This is a Hubble image. We have what looks like a ring galaxy, it looks like a disk galaxy, but it just has a giant ring in it. And what we know has happened here is there's a galaxy that you can't see. It's off to the right-hand side. The galaxy simply passed through a disk galaxy and left a giant hole in it, and then pushed all of its material out into a ring. The entire galaxy is blue now because you've effectively compressed all of the dust and gas, and now there's a big star formation event occurring. And so a lot of times rings in galaxies are the result of either pulling material out of a galaxy or passing through it and leaving a hole like that. So, yes, Raymond.
So what's a wormhole?
Well, that's a totally different idea. Yeah, no, that's not related to galaxies, it's related to black holes. But, yeah, anyway, not similar.
I was wondering if that was what.
Yeah, no. Now the tails, a very famous pair of galaxies that show these tails is a pair of galaxies called the mice. That looks like this picture over here is a contrast map. There's two disk galaxies with tails on them. This one has a tail that goes directly back, and this has some sort of some kind of aura coming out of its head. I don't know what that is, but you just call them tails. And astronomers have been able to model why these tails occur. Oops. So the galaxy in the picture on the top here, the galaxy that's on the right was originally on the left, moving to the right. The other galaxy was on the right, it was moving to the left. And as they pass each other, they pass close enough that their mutual gravities will change their trajectories and actually pull them back towards each other. So this galaxy that's indicated in blue was on the left here, moving to the right, experienced a gravitational pull by the other one, and kind of swung back around. Now, when it swings back around, the stars that are in that galaxy will not feel the same gravitational pull, because gravity has a distance dependence on it, and there's a tidal interaction. Some of the galaxy will continue along its original path. These out here are stars that did not feel a strong enough gravitational pull back. So the galaxy gets stretched out, and some of it just continues along its path. That's why this tail formed here. It's because some of the material still is moving in that direction. Same thing with the red. It was on the right here, moving to the left. Mutual gravity pulled it back, and some of its mass did not feel a strong enough pull, and that was strewn out in this tail-like structure here. Same thing happened back here with the Antennae Galaxy. These tails are the result of a tidal interaction. The direction of those tails is the direction those galaxies were moving to begin with. Most of the material is pulled back, some of it stayed out like that. And so those are really common features that we see. As I mentioned, I showed you this slide earlier, but we like to model this stuff. We want to see if we can reproduce the pictures based on initial conditions and then fast forward in time and see what things look like in the future. I'll demonstrate one of those right here. This is a famous series of images from Hubble of galaxies that are merging together. And the mergers are all happening in different stages. These are totally different systems in different parts of the universe, where we're seeing these galaxies come together. The one on the upper left here is likely going to be a ring galaxy because it looks like that's kind of going through in some way or coming in. These ones are just beginning to collide. Anyway, there was a group of researchers that took these images and through a single interaction was able to reproduce every single image here through one interaction. So let me show you that and explain the significance of this. Maybe I can find it by searching. Okay, so Hubble merger. Oh, my keyboard is not working today. Nope. All right, I'm just gonna grab it here on. Okay, so again, this is simulations trying to reproduce the Hubble images. What's impressive about this is this single system that they just mouse. So it's really remarkable that they're able to take a single simulation and reproduce the same images, basically. Now, what's good about that is that it signifies that while you see a lot of variety in galaxy shapes and sizes because of interactions, the mechanisms are probably pretty simple. And all the variety that you see is simply a matter of time and field of view, meaning what time are we seeing this and which direction are we looking at? If you take two disk galaxies and merge them together, they're always going to look like this probably. It's just at what point do you see the interaction and in what direction do you see it? Can't show you that. It's classified. I'd get in big trouble. And don't bother looking that up on your own. Somebody will bust through the door, take you away in handcuffs. You'll never be seen again. That's why. That's why Mankind will end. Everybody will look it up, and then it'll be taken away. All right, so one of the major results of these galaxies merging together is what we call a starburst galaxy. Starburst galaxy, now these are different images taken on different wavelengths of just the entire galaxy engulfed in a major star formation event. The structure is very difficult to make out because the entire galaxy is undergoing a lot of star formation. So they generally look very irregular in appearance. These don't look like ellipticals. These don't look like spirals. That one kind of does, though. But they're very bright infrared wavelengths because a lot of the dust and gas has been excited. They're usually very luminous galaxies because they have tons of O stars and B stars and A stars. And there's some interesting things that happen as a result of these. When you merge two galaxies together, not only do you use up a lot of the dust and the gas, but sometimes you activate the galaxies. Okay? Now what activate the galaxy means is this. We know that we have a black hole at the center of our galaxy. And when we look at a lot of other nearby galaxies, we see the same thing. We believe that every galaxy has a supermassive black hole at the center. So if you mix two galaxies together, you're likely going to piss off that black hole. And that's what happens. So there are a certain percentage of nearby galaxies, it's about 10%, which is the same number for irregulars, of galaxies that appear normal in most respects, except their black holes are activated. Okay? We call these things, well, we call the galaxies themselves active galaxies, but the cores are called AGN, active galactic nuclei. Now, this was a big topic in the 60s and 70s in astronomy because we had no idea black holes existed in galaxies. We just observed the fact that some galaxies contained cores that were about the size of a solar system, but were far more luminous than an entire galaxy. And that was obviously very strange to see. Now, this picture here, there's a galaxy here. You can't see it because it is outshined by the core of the galaxy and these two hot spots over here. This is a black hole with an active accretion disk. It's an active black hole. There's matter currently fallen into it. As a result, the matter that falls into it falls at almost the speed of light. It either falls into the black hole and sort of spews out tons of X-rays and gamma rays in the process, or it gets ejected through jets that occur on either sides of the object. These are jets of material that are being shot out of the accretion disk. So what happens is most material spirals into the black hole, it's gone. Some of it gets caught up in a magnetic field and spins above and below and then basically gets shot out like jets. And we've talked about this before for star formation and other things. This is very common when we have accretion disks and jets, but these jets are nasty blowtorches, basically. They move at almost the speed of light, and they eventually collide with the intergalactic medium. I mean, this looks like a blowtorch because it basically is. And these are two really hot spots where the jets are colliding with a lot of gas. Overall, this is probably, this is larger than a galaxy, but that spot there is tiny, very, very tiny, actually. And when you look at that spot, you notice that it doesn't have the same features you would expect for a galaxy. Now, the picture on the upper left here, this is what's called a Seyfert Galaxy. This is a spiral galaxy with an active center. When we look at that active center, we expect to see absorption lines, okay, something like this, because the spectrum of a galaxy would simply be the combined light of billions of stars, which is normally very confusing, because you can't, if you mix together a billion spectra into one, it's going to look like a mess, but it's still going to have absorption lines. When we look at the cores of these things, though, we do not see absorption lines. We actually see that we have an emission line spectrum. There's no absorption lines, there's emission lines, which means it's a hot gas that's produced in the emission lines. Anyway, they're extremely bright. They have a very high variability, which means they can change their brightness really quickly. How quickly these change their brightness indicates how small they are. The faster they vary, the smaller in brightness they are. Okay, you cannot vary faster than the light distance it is. So let me give you an example of that. Our solar system in length, the diameter of it, is something around maybe the solar system proper, basically, 2 light hours in distance. Okay. So if something were to magically happen to our galaxy, our solar system, say just the whole thing exploded for some reason, just exploded, the whole thing at once, a distant light source would not see an explosion necessarily. They would see our solar system gradually become brighter over the course of 2 hours, because the light takes time to go across the galaxy. You get a signal that something's happening. That would come from like the front of the solar system, one side of it, and then by the time the light from the other side got to the source, 2 hours would pass. So you'd see a gradual rise in brightness over the course of 2 hours. Well, some of these things are just a few months, which is, again, that's the solar system size. Okay, it's not even a full year, so it's not even the distances between stars. So we know today that these are supermassive black holes that are activated. Whereas before we had no idea, because they actually come in different appearances. These are all pictures of spiral galaxies with active cores. Now, all of these galaxies are seen face on. We actually look down onto the accretion disks of the black holes, as opposed to something like this. This is another type of AGN, but it doesn't have the same kind of appearance because we're seeing this galaxy edge on. And the core is being obscured by all the dust and gas in the galaxy. Instead, we just see the jets of material on either side that are being shot out from the core. That's all we can see. We call these things radio galaxies because these lobes emit tons of radio waves. In fact, the largest structure in apparent size in the universe is a radio galaxy. These lobes are like larger than the size of your hand up in the sky. I mean, they're huge, actually. So now we know today that all different varieties of active galaxies all come from the same thing. You have a black hole at the center, spewing out jets of material. When you look down onto the disk, you generally get these Seyferts, these spirals with the active cores. You can't make out the jets very easily. On the other hand, radio galaxies are ones where you're looking at it from an edge, and you can't see the core very easily, but the jets instead of stand out. Okay. Now, again, what we do is we say, okay, well, what's going on here? We look at a lot of these galaxies and their environments, and we see the evidence of interactions. This is a Seyfert Galaxy here. There's a tail coming off of it over here. These are pieces that have a very similar space motion, indicating they're probably part of that and broke off at some point. That's an active galaxy as well. This radio galaxy over here, I forgot, I don't have the bigger picture to show you this one, but this is likely an interaction as well. So what happens is when you take two galaxies and you merge them together, or you disrupt them majorly in some way, as one galaxy passes through another, that black hole is going to carve out basically a big chunk of it as it moves through the other one. And that's going to create a lot of extra mass that will fall into the black hole and create this big accretion disk. And so the fact that 10% of galaxies today have active black holes is in line with the fact that about 10% of galaxies interact with each other. And that's how black holes get fueled. So what could very well happen is when our galaxy Andromeda combine together and we convert into elliptical, our black hole might get activated. And the two black holes from Andromeda and us will probably come together. And so it's very likely that it will be activated and we'll have a massive, active galaxy as well. All right, anyway, any questions about that? Yes, Randy?
So how do quasars come into it?
Good. I'm glad you asked. Okay, so quasars are similar. They're active galaxies. There's a couple differences to them. This picture here, this is a star on the right-hand side. This is a star that's in our galaxy. And usually when you have images of stars in our galaxy like this, you have these spikes on them. The spikes are called diffraction spikes. They come from imaging the star in a telescope. And it's usually because they're so bright, they produce these fringe lines, basically, is what these are. This is a quasar here. It looks identical to the star. And so for a while, back in the 70s, astronomers thought these were stars in our own galaxy. But when you look at them in spectra, they make no sense at all. They don't have absorption lines, they have emission lines, and their spectrum looks bizarre. So it's not a star of any kind. In fact, the name quasar comes from quasi-stellar radio source. That's what it means. And what we find is that these are actually active galaxies, but active galaxies as they existed in the far past. We have no quasars around us today. The most distant quasar is something like 1 to 2 billion light years away. So these are things of the past. And what these are active galaxies like Seyferts and radio galaxies, but they're far more powerful because when the universe was smaller in size and collisions were more common, even more matter got thrown into the black holes. And so these things they're far more luminous than the stuff we have around us today. In fact, this quasar here, I actually saw this talk that a guy was giving about quasars, and he was just doing this sort of thought experiment here. If you took that quasar and put it where the sun is, in our solar system, okay, a planet like the Earth, if it was placed at the distance of Pluto, would have its oceans vaporized by that quasar in 1/5 of a second. Wow. That's how much energy is being produced. It's an enormous amount of energy. Everything in the immediate vicinity of the quasar is, it is annihilated. I'll use that word, annihilated, which means what we're saying here is matter is converted to energy. It's so energetic. So these are, now, this is a galaxy that is on the other side of the universe, but it's as bright as a star in our own galaxy. That's insane, right? And when we look at these things, we see that they're redshifted dramatically. All of their spectral lines appear at longer wavelengths, indicating a redshift. Okay, this is the pattern for hydrogen. The pattern for hydrogen shows up here with a redshift. Now this right here, this 0.158, that basically indicates how fast it moves relative to the speed of light. That's 15. Let's see, what is that? Something like it's like 15% the speed of light or something like that. It's extremely far away, moving very, very fast, actually. All right. So when we study these in some detail, we do, if we look at them very carefully, we can make out the host galaxies for them. Again, the host galaxies are always showing interactions, current interactions, mergers taking place right now. So these are fresh AGN, fresh, like just recently made. A lot of the AGN we see today actually will probably form further in the past, and over time they dim down in luminosity. This is the creation of brand new ones. And they actually have some really crazy characteristics to them. One of the characteristics they have is, let me give an example here. This picture here, we have two quasars, here and here, and there's a galaxy, nearby galaxy, right above that one. When we study these two quasars, we look at their spectrum, we see that they're identical. Totally identical. Same emission lines, same places, redshifted basically the same way. And when they change in brightness in the exact same way with a time delay. One will check, this one up here, for example, might change a week later than the other one, which is very odd. And we actually see other characteristics of this stuff as well. There's another system down here, 4 quasars surrounding this galaxy. They all are identical in appearance, and when they change in brightness, they all change the same way, but with different times. This one might happen first, this one's a day later, 5 days later, 2 weeks later, something like that. And that was really strange, but we understand what's happening now. This is one quasar, one extremely distant galaxy, that's being gravitationally lensed by a nearby galaxy. And so these two images you see here are not where the quasar is located. The quasar is directly behind this one. We can't see it because it's directly behind it. Instead, the bending of the light makes it appear that the images are above and below. And this light path may be different lengths. For example, that light path is clearly longer because the image is further up above the galaxy. This one has a tighter path, so it's a shorter distance, and that's why we see a time delay. Okay, the time delay just corresponds to what's difference in the length of path. So 4 galaxies here, again, 4 different light paths. This one here, same deal. This is a barred spiral surrounded by 4 quasars. Okay. Initially, when they discovered these things, throughout a lot of the 50s, 60s, and 70s, mostly 50s and 60s, there's a debate. Big Bang model versus a steady state model of the of cosmology. And for a while, the Big Bang model was the leading model because all the observational evidence for it was supported by all these Big Bang, by expansion, all these other things. When these were discovered, a lot of people that were supporters of the steady state model believed that this was support for the steady state model because they thought that this galaxy in the middle here was actually creating these quasars. It created them and spit them out. And that's why you always see quasars surrounding galaxies. These are quasars created by that one. These are quasars created by that one. Turns out all those people were nuts, totally insane. I actually went to a talk by one of them when I was still in grad school. It was like this old lady. She was like in her 80s, and she was still like, I'm right. Steady state model is it. And she presented evidence for this, and it was really weird because I went to this talk and nobody was paying attention to her. And she was an important figure in astronomy in her heyday. It was Margaret Burbage, big-time astronomer. Everybody was ignoring her, and so I poked the guy next to me, like, what's going on here? Like, this is Margaret Burbage. And everybody's ignoring her. She's like, well, she's given a steady-state argument. I was like, oh, okay. Which means she was presenting evidence that she believed was against the Big Bang, which at that point in the 2000s was like a joke. There's so much observational evidence for the Big Bang, any alternative theories not taken very seriously now. Anyway, last thing I want to say about these is going back to the slide here. Quasars are a really big deal because quasars are extremely bright, meaning you can see them on the other side of the universe. They give us a lot of information about the history of the universe. They give us a lot of information about gravitational lensing, dark matter, because that all happens in there. And so quasars are used quite extensively. I think one of the most important things about quasars is the evolution aspect. Quasars are a thing of the past. They don't exist today. We have analogs for quasars that are these active galaxies. They've just basically calmed down since their earlier times. All right. I think that's all I'm going to say about galaxies. Like I said, when we come back, we'll actually get into the Big Bang model. And we'll talk about aliens too. So anyway, have a good Thanksgiving, and I'll see you after the break.